don't see my screen or there's anything that you don't see, you have to use your mic, because otherwise I won't see your face. Okay, cool. Thanks, Christine. So thanks so much, guys, for joining us. And hopefully all the problems are now being fixed. So we're gonna present our work, which is titled as a spy movie from the 60s. The embedding came in from the code. It's gonna be me and Christine. And thanks more for joining us. A couple of words about us before we start. So nice to meet you, and thanks again for spending some of your time with us. So we are. I already gave a talk at this meetup, and it was super funny. Back in the days where you can actually meet people. So you already should know who I am. But I was the co-founder and CTO of Tuzo, a startup in San Francisco. That was our basically business plan, and we went through basically all the 4 phases. Tuzo was acquired last year by Canadian unicorn Kobeo, and now I'm the lead scientist of Kobeo after the acquisition. The other speaker of this talk is Christine. She's gonna speak about the more technical part of our work, and she's a machine learning engineer at Kobeo, and she's co-authoring with me. She's been co-authoring with me several papers in some top-tier conferences in machine learning and NLP this year. About our employer, which we all are thankful for all the data and all the possibilities that we have to experiment with. It's Kobeo. You may or may not Kobeo, depending on basically which side of the world you're on. If you never heard of us, it's a Canadian-born company with offices in Canada, of course, the United States, London, and Paris. And we basically do AI search recommendation and similar services to a bunch of companies. Some of them are mid-sized companies, some of them are Fortune 500. Kobeo rose to fame last year with raising more than $500 million and making it officially a unicorn, which is a private company with a valuation of more than $1 billion. We have more than 1,000 customer deployments, and I think now we have actually 600 employees. This might seem like it's already cool. So what we do as a company, and it turns out to be very important for what we're going to explain, is that we actually sell our tools. So we do not own e-commerce or any front-facing business, but we sell our tools to people that own, for example, an e-commerce or a website, so that they can offer to the final shopper like a theyre experience. So today we're going to talk mostly about embeddings, which are a fancy word to basically describe the way in which neural networks understand and process products. Why products? Well, because what we're going to see today is mostly about what people do on an e-commerce website. Since I don't know how many of you are familiar with the concept of embedding in general, I prepared just 4 slides to kind of introduce the problem. If you already know about this, you can you can go and get a coffee and come back in 3 minutes. So embeddings come from, they've been popularized in NLP, natural language processing. Why? Well, there was this thing we used to do in NLP for a lot of years, which is we have to transform somehow words to vectors, because computer works with numbers. And for the longest time, what we did was do this sort of one-off vectors to represent words for computers. This is an illustration with 4 words. You have dog, cat, phone, and play. As you can see, the vectors here, they're basically like a list of zeros and ones, and you can see that the 1 fits position in this vector, which is the way in which we represent different words in this case. Well, there are 2 main issues with this representation. First one is that it's not very practical, because if you imagine instead of having 4 words, you have 40,000. You realize you need very big vectors, which are mostly empty to actually deal with this vocabulary. The second problem we have is that looking at 2 vectors, like for example, dog and cat or home and play, is very hard. It's actually impossible to tell if they are related. As in an ideal world, we would want a representation of words such that dog and cat are somehow, whatever that means, more similar than, for example, cat and phone. The way in which these 2 problems have been solved is with word embedding, which is low-dimensional representation. So instead of having these gigantic vectors, which are very sparse, you have low-dimensional dense vectors of words, and they are built through what is called the distributional hypothesis. The distributional hypothesis is basically the idea that the meaning of a word is determined by the context in which it appears. As we always joke, is the machine learning equivalent of the saying, you know a lot about a man, but a company. If you see the plot here, we train a small word-to-back model on I don't remember which available corpus. As you can see, we color-coded these dots. Each of these dots is one of the words. As you can see here, the algorithm is very good at clustering together words that are basically pertaining to the same type of topic. You have countries, which is the blue one. You have cities, which is the green one. You have, for example, food, which is the purple one at the bottom. What you can see here is also that the relative position of these topics in the space actually reflects the underlying semantic meanings that we as humans recognize. For example, countries and cities are very close to each other, while countries and food tend to be very far because they're like semantically less related. So so as I said, words instead of being this gigantic sparse vector are now low dimensional dense vector, and then the dense space that we produce somehow mimics the underlying semantics of the word. So closer words in the space tend to be closer words in the semantic space. Now we go from word to vec, which is a small introduction of embeddings, to product to vec, which is the version with products. So exactly as words, products are discrete entities, right? If you work in e-commerce, or even if you're just a shopper in e-commerce, we can easily imagine how products appear when they're actually loaded into an e-commerce site. They're basically a table, right? So these are called products, and this is basically what happens, in any e-commerce. There's like one row for each of the products, and the product will have, an image and, for example, some data, like the brand, the price, the sport, and so on and so forth. In this case, and we're going to work today mostly with the sports apparel catalog. What is the problem with, conceptualizing products as basically a list of items? Well, it's the same product as with words, right? These are very discrete representation, and they're very sparse, and they're not very neural network language. Luckily for us, there's an easy analogy between words and product, which is the session. Let's take these two anonymous users, one, the girl on top and the boy at the bottom. They go on this sports apparel website and they start browsing different products, right? Like the girl, for example, clicking on the tennis sneakers, then a tennis racket, then a skirt, and so on. What we may call like a tennis-related session. So she's interested in tennis, and the man, the boy at the bottom, is actually interested in soccer. What is the analogy? Well, the analogy is the word to vec. Remember, word to vec, the fundamental intuition is that the meaning of a word is basically a function of the context in which the word appears. And prop to vec is actually the same. So we have to swap in the concept of words in a sentence, like the cat is on the map, with the concept of products in a shopping session. So if you remember, the products are actually seen in sequences, as we saw in the previous slide. You basically can bring the exact same model they use for word to vec to prop to vec. Once you train them, this is actually a representation of sports apparel catalog from real data. This is a three-dimensional representation instead of the two-dimensional I was looking for. As you can see here, we kind of get the same kind of phenomenon that we observe with words. Each of these dots is one of the products in this catalog, and they're color-coded by the sports activity, which means that products that have the same color are about the same sport. So, for example, the purple one is running, the light green one is soccer, and so on and so forth. As you can see here, exactly as in the case with Word, the algorithm is very good in clustering together products that are somehow semantically related. So what we usually, when we started this talk, we described products as basically discrete entities, like lists in this table as we've shown before. But now that we have a space, we can actually place the very same product in this space. As you can see here, they each occupy very different regions of space depending on the sport they're about. And again, why they're important? Well, that is important because now that every product is positioned on this space, we can kind of map the sequence. We can kind of map what this girl is looking at as a path, as a journey through this space. Which means that different users that are browsing in real time on e-commerce will actually visit different regions of the space. This is very important because this lets the machine doing all sorts of inference and personalization. Again, this is very intuitive if you think about it. Think about the real world, not the product space, but the actual geographical space. By the fact that somebody goes on vacation, let's say in Honolulu, instead of the Rocky Mountain, you can tell a lot about their presence, right? And this is exactly what happens in e-commerce. When a neural network observes, like the girl or the boy moving in different directions in space, this tells a lot about about what they actually want to buy, and it means that we can do better inference and better machine learning models. So product embedding, which is low-dimensional representation of products like the one we built here, are very important because they can be used across the entire spectrum of this e-commerce service: recommendations, type ads, search ranking, and so on and so forth. And now that we know why they're important, we're gonna go back to some more references again. I'm gonna let the screen to Christine, so she's gonna actually go into the details on how do we train good embedding. One thing that I forgot to mention in the beginning, I think the talk is being recorded right now, but also the slides are gonna be freely available. So there's a lot of links and things you can click on the slide that gets you to some paper in the literature or some of our own papers. So if you lose some details or if you have questions about particular technical things, you can either ask them at the end or you can just go to the slides and like after the talk. Let me stop sharing so Christine can go and share her own. Thanks.
Can you see my slide?
Yes, we can. Thanks.
Yeah. So with Jacopo's talk, we all know what is a product space, right? So we train our product model and then we get a space back. And inside of this space, all the products should be distributed across different regions. And of course, similar products should be closer in the coordinates of this space. However, with this, how can we tell if indeed we can get a good representation of the product? And by good space, I mean this space should be good at capturing all kinds of product characteristics and similarities. And of course, we should be able to tell something useful about the user intention based on this space, right? So the question now is, how can we tell between a good representation and a bad representation? This is quite tricky because actually for projects, it's really not easy to get a good representation. And because we know to have embeddings, we have to train a small neural network, also with user behavior data. And once we start to talk about training our model and with different data, we know we have many different things that can actually affect the performance of the model we get. So for example, in the case of project, we have a bunch of hyperparameters we have to consider. So here you can see the negative sampling here is defined in which way we are going to sample those negative samples, and also iterations here for how long we are going to train the model, and down here minimum count that defines which are the products we are going to discard because they are too rare and too unpopular. And last one for the window size, so how we are going to define which products form a pair of positive examples and which products belong to negative examples. So with all this, actually, somehow with the bad hyperparameter setting, you may get a very bad representation of the project. And what can we tell from my visual inspection? Actually, on the image here, those are two product space we have built. And to mention again, the colors actually represent four categories of the product. On the left-hand side, you can see our fantastic embedding. It's easily to see that based on the color, you can see the products are well organized in the space, and the different types of products actually occupy different portions of this space. And however, on the right-hand side, we have a really, really bad embedding, right? You can see everything is mixed here with no clear separation. And of course, you cannot tell much with this bad product space. So we also want to run something really simple to confirm our visual inspection. So what we do is we actually train a small multi-layer perception neural network to do a classification task. So for this, we ask the network to learn a mapping between the product embedding and the fourth category. So the intuition behind is if we see the neural network is very easily, is very able to predict the fourth category based on the input product embedding, That means our input product embeddings are very good at providing some meaningful things about the product, right? And actually, after the training, we can see the results. The fantastic embedding on the left-hand side actually give much higher accuracy compared to the bad embedding at the right-hand side. Because you can see a number here is 0.9 versus 0.3 in terms of accuracy. So this, we can confirm the video intuition behind it. So now we are saying that it's really, really critical to have a systematic way of doing this evaluation because we really need to ensure the quality of the embedding. So to have a systematic way of doing this, we are offering our recipe here. What we do is first, you can produce a lot of embeddings using different hyperparametric settings. You can set a range of the parameters, like you can choose the range that you like, you think makes sense to experiment. And second, you are going to evaluate the quality of the embedding using a downstream test. And finally, with the scores, with the metrics that you get from the downstream test, you will be able to determine the best and the worst embedding. And to be more detailed, what is the downstream test we are going to use? Here we are going to use the next event prediction test. Actually, this is a quite famous way of evaluating embedding, and also the next event prediction test is quite commonly used for recommendations and the e-commerce industry. So for this, we are going to take a user session, and we are going to take all the products that the user has interacted with, except the last one. So the last one here is the helmet. And we are going to see if the model is going to take all the products before and predict the last element of the session. And to implement this, we can just take the average embedding of the three products on the left-hand side. And once we get this average vector, we go back to our product space, and we will generate some nearest neighbors of this average vector. And then what we do is we just check if the helmet can be found among the nearest neighbors of this vector. And here we are testing our model using two different shops, shop A and shop B. And you can notice here, actually, different shops might require different product parameters. That's why it's important to follow our recipe whenever you have different data and different experimentations. However, you can see here, no matter what is the testing shop A or shop B, with some standard metric like NDCG, you can generally compute this using your downstream test. And based on those numbers, you are also going to get an estimation of the best and the worst embeddings through the evaluation metrics. So with those metrics, you are able to determine among all the millions of product spaces you produce, which one is the best and which one is the worst. And actually, if you are interested, you can go and check our paper. We have published it bigger conference this year on the e-commerce track. And also, we also publish more blog posts on our website. So there should be much details explaining this topic. And now we know our recipe to produce product spaces. And in theory, like that, from what I talked about, if you follow the recipe, you should be able to have a perfect product space back, right? But you may wonder, so why we should still fix or improve the product space? And actually, we still have a problem here. Even with a very, very decent product space, because of the training and because of the back propagation of the product, you can still get very bad quality of the embeddings for those rare products. And by rare products, I mean those products that do not get much user interactions. They are very unpopular in the shop. So this problem for those kind of rare things with the data actually is a well-known problem in e-commerce and also in recommendation. This is called the post-start problem. And clearly, as I stated before, our portfolio also suffers from this code stuff for this. So we really want to find a solution in this case. And to be more concrete, you can see those two concrete examples. If you build a product space and then you take this space and you go inside it to see what happens to the product, you can observe two different things. Like on the left-hand side, if you take this sneaker is, if we assume like this sneaker is really, really popular product in this workshop, then we are going to see those two nearest neighbors. You can see they are all sneakers and they really make much sense for human inspection. However, on the right-hand side, if you choose a real, like really like unpopular product, for example, this GPS watch from the sports shop, and we all know like the GPS watch is very less popular compared to the sneaker. And for the GPS watch, you are going to see those two nearest neighbors. Like one is also a GPS watch, so it's good, but we are going to see those two like really strange nearest neighbors. One is like sizing device, and another one is the GoPro camera. And as you can tell, they are really, really like irrelevant to the GPS watch. So you can see like there's a problem for this unpopular product. And plus, not to mention those new products that we are going to release in the shop, right? For those new products, you don't have any interaction. So like you don't even have a vector in the space. So what we are going to do with this, to find a solution, our solution involves content embedding. So actually, what we do is we take all the popular products, and we are going to take the textual metadata of those popular ones from the catalog, of course, and we are going to run them through like a model like sentence first. But of course, you can use your favorite content embedding model. And at the end of the day, the goal is to have a content vector for this product. And then we are going to train a neural network to know a mapping between the content vector that we produce with the first model and with the product to vector in our product space. So a mapping from the content vector to the post vector. And the thing we want to know is we want to the neural network to be able to, given what is there, for example, taking the sneaker, given what is in the catalog for the sneaker, we want the neural network to predict what position the sneaker might occupy in this product space. So once we achieve this, we have a very decent mapping. What we do is we just apply this mapping to real and new products. So we have this GPS watch again. So we go into the catalog, we see what is there in the catalog for the GPS watch, and then we are going to apply the mapping, and the mapping will provide us with the post vector of the GPS watch. And that's how we just construct some simulated vector of those real products. And also we want to know that it works with our mixed model data. So again, we are going to use our next event prediction task. So just to remind you, the next event prediction task, so we are going to take all the previous products. We are going to just see if the neural network is able to predict what is the next event that the user is going to do. So as you can see, also just to also mention, as Jacopo talked about, Kobeo actually we are a multi-tenant provider, so we are actually providing our solutions to different e-commerce websites, and that's why like it's really important to ensure that our solution is robust across different shops. So for experimenting and testing, we are going to use shop ABC, and they are really different e-commerce shops, and they are different in terms of graphic size, and also they are very different in terms of their destination. However, with all those results, you can see on the middle column here, you can see the word original. That means we are going to use the original product to back space. We are just going to train the post back with the behavior data. However, the right-hand side, you can see we are going to use our mixed space. So by mixed space, I mean we are going to still keep all the post back for the popular product. However, for the real product and for the new product, we are going to switch to our method. We are going to generate their embeddings using our method that I just talked about. So what are the numbers you can see? For the real product, our mixed space actually vastly outperforms the original space. You see the numbers, the results are actually 2 to 10 times better than the original space. And that can prove that our solution works across the shops. And with this, I want to mention a point that I didn't mention before. And however, this point that I'm going to raise is really intuitive if you start to consider yourself as an online shopper. So the thing is, if you go online and all the recommendations are good and the prediction is correct, everybody is happy, right? Because we get correct as a good prediction from the model. However, when the model is making a mistake, actually it can be run in 2 completely different ways. As you can see, those 2 use cases here on the top. If the target is like running shoes, the prediction is not exactly this pair of running shoes as the target, but you can see the blue shoes is still a pair of running shoes, right? So in this case, the model is making a mistake, but it's running a reasonable way. And if I'm an online shopper, I will still stay on the website and keep browsing because I feel this is quite normal for a machine learning model. However, for the second use case, if you see the target is a yellow shoe, however, the prediction is completely like irrelevant. It's a pair of clothes. In this case, if I'm a shopper and I see this, I might really like just quit the website because I might feel very, very, very frustrated with the system. And this second case actually means the machine learning is wrong, but in addition, it's wrong in a very unacceptable way for user experience. So we really want to distinguish these 2 differences. However, if you remember, like if we use some standard metrics like NDCG and hit ratio, and those standard metrics used by academia and the industry, actually those metrics can really not tell the difference because for those metrics, if it's correct, it's a +1, right? And if it's not correct, it's a -1. There's no differences between this like clothes and running shoes. So for us, we don't want to just abandon. We also want to keep track of those like very small differences in terms of model behavior. And what we do here is we are going to compute the cosine distance between the target vector and prediction vector. As you know, like cosine distance is a very good metric to measure the vector similarity, right? So if we compute the cosine distance, we are going to see how similar, what similarity is there between the target and vector. And again, in the table, you can see the result. In the result in the middle column, again, we use the original space, and right-hand side, we use the mixed space. You can see our mixed space is actually always better than the original space, again, across 3 different shops, because the cosine distances are way smaller. That means even with the mixed space, the model is still making some mistakes, but it's okay because the cosine distances are smaller. That means the vector of the target and the vector of the prediction are closer together, and that means at the same time the online shopper will going to get a better user experience and a more coherent experience. And want to know more? Actually, we have published a paper at Wexis this year, and this is really a joint work. And also, I want to give a special thanks to Federico Bianchi, and he is our NLP expert from Bocconi University in Italy. So if you are curious, you can get more details there. And also, we have written a blog post explaining this topic. Yeah, now I will pass it to Jacopo.
Thanks, Christina. I think I forgot to tell you that Bianchi is the Federico spelled Bianchi and not Bianchi, but yeah. Let me share my screen. Yes. My fault. I forgot to tell you, how we say that in Italian. One second. Let me share my screen again for the last section. Very nice. Okay. Yes, you should see my screen. Hopefully. Yeah. So yeah, thanks so much, Christine. So we went from a brief introduction to what product vector are with analogy basically to the way more famous word vectors in NFT. And we mentioned, if you remember the slide at the beginning, that product vectors are actually central to many problems in the e-commerce space, ranging from in-session recommendation, personalization, type ad, and so on and so forth. And we actually have been successfully applied this very simple concept, if you think about it, the idea that products can be represented in a space on a map and not just as discrete entities. We took this problem and we kind of made we took this approach and we made like several studies and several benchmarks this year in many different use cases. We didn't do it by ourselves. So Federico is one of the person that of course helped us the most doing this year, but there's a lot of other people that we want to thank you. This is like a small almost several of them. I guess I think one of them at least already was a speaker at this very same meetup, which is Piero. And I mean, if you guys, if the organizers like me, there's a lot of people here you can invite to give like fantastic talks. The general message here is that, well, all the things that have been accomplished by Kobeo, and in particular by our team, are actually like a network effort, as in we strive to involve people from other research institutions, from other companies like Uber, other universities and institutions like Microsoft Research to kind of come and share part of their roadmap with us, so that we can work on use cases that we both like. This year has been been pretty priority this year, and we presented work in we're gonna present our work paper in like in 2 weeks. We've been at the web conference, ACL, theyre, AKI, and many more. If you want to know exactly about what we've been doing, there's like a blog post you can actually see with all the contributions that we made. And the point about this is not really to bragging about what we did, but we really like to work with people from other institutions and other universities, and we have very, very good policy on data sharing, which means that if you're curious and you have like models or you have theories or you have ideas on how, I don't know, personalization models can work in e-commerce or information retrieval can be improved, like anything that you can think of that is somehow related to our use cases, there's a ton. We have very good data that we can share under a very friendly research agreement so that we can actually do something together. If there's something we should be proud of, and designs we're proud of about this 2020, when I think it's been very strange for everybody, is the network of friends and researchers and communities that we kind of built around this idea that if we have good data that we can share, in anonymous and obviously totally legally compliant fashion, that will actually boost the research in the field that we care about much more than if we keep all this data and all this knowledge to ourselves. So while our outreach capacity is still somewhat limited, sure, we're a unicorn, but we're nowhere close to be Microsoft Research or Uber. We really strive to involve many people in our roadmap and to try to work with them together. So if anybody that's joining us today thinks he has some idea that you want to share, please reach out. We're very easy to reach through LinkedIn or email, and we're super happy to sit down with you and see if there's something we can do together. Thanks so much. If you have questions either about the technical details of the solution that we presented or the general roadmap that we have for commerce, please, we are at your disposal. Jamari, I don't know if it was you, but it was just like this noise.
I'm talking to this other. Let me talk from this other account. I think there are a few questions in
in the chat. So maybe you want to go through them and try to answer some of those. Sure. Sorry. Yes, I didn't have my chat open. Yeah. So Also, yeah. I guess everybody see them, or maybe I'm just gonna read them out loud for the recording. So it's part of what you're showing already implemented in terms of flow recommenders. Elizabeth asked. The answer to that is honestly, I don't know exactly what is in terms of flow recommenders. So I don't know if Christine has a more specific opinion. The focus here is the focus for us was mostly to produce product vectors that are like of a certain quality because they're used not just for recommendation but for all sorts of NLP and personalization tasks. So sure, maybe I'm sure there's some embeddings in the sense of a code, but the idea for us to produce this type of embedding is that we can use them across the board. So I would say it's a slightly more general use than just recommendation alone. Ricardo asked, was the hyperparameter negative sampling? Christine, you want to answer that?
Yeah. So for this, I know it's a hyperparameter that I mentioned in my talk. And because for ProTrack, you are going to train a network with positive and negative pairs, right? For positive samples, it's really straightforward to get. We just define a window size, and all the products within that window can be considered like pairs with positive pairs with each other. However, you can imagine there's like infinite number of negative things if you need to sample the negative one. So you can sample like one product and then with another product that is really far away from this product, and those two can form a negative pair. So actually, with this hyperparameter negative sampling exponent, you are going to define how are you going to sample the negative pairs. So actually, this is the number that determines you are going to sample proportionally to the frequency of the product or inversely proportionally to the frequency of the product. So if we go to our paper and also other related literature, you can see by playing with this parameters, you are going to get some difference in terms of model performance.
Yeah, I think one thing that is important to mention that we made the point in our paper, but there's a bunch of other papers that make that as well, is that the standard parameter, like we train Protobag with Jensen, right? Which is what probably most of you use to do word embedding generally. So it's literally the same code as the word embedding part, but the default parameters that are in Jensen for the NLP case tends to be very different from decent parameters in the software space. So just if you go and use the same code as we do, just make sure that you don't really use the default because you may not get the best results. Ricardo has another question, which is, have you considered using graph neural network? The answer is not in particular, as in we do not have a graph. I mean, it's a bit of a trick question, but let's say for simplicity, we do not have a graph representation of products and users, and maintaining that across all our clients, which like hundreds, may be a bit impractical. So we have some knowledge graph initiatives, but they're not specifically related to products. So we don't have any benchmarks against embeddings produced by graph methods instead of simple session-based methods. Andrea asked for the NEP task. Are there other ways to combine product embeddings besides averaging? The answer is yes. We actually have also, in the paper, we also have the version with the LSTM, which is, you basically train a vanilla sequence based neural network in which you, instead of feeding the averaging of the previous product, you basically feed all the products and you have to predict what's going to be next. The relative, so when you run this LSTM instead of the averaging on the hyperparameter evaluation that Christine was mentioning, the relative order, like the general gist is basically you get very, very similar results, not exactly the same. Here we expose the average because it's just faster to compute and easier to understand. But we didn't find particularly much difference in what this method finds. Christine, am I correct? Okay. Manuel asked one question. Do you also consider exogenous variable to get embeddings, for instance, season? In summer, I buy a football plus shirt, correct. Whereas in winter, football plus leg warmer shouldn't displace a football in very different location in product space. So yes, Manuel. So the seasonality is a big issue in commerce in general. What happens in practice is that if you imagine providing, embedding, let's say we're Kobeo and we provide again like these services to, I don't know, Nike.com. Let's take an example. So Nike users, as the year changes, as the season change, will start not looking for shorts anymore, but for leg warmers, which means that when you trade these on a schedule, your window basically of training will just shift, and that means that basically, like leg warmers are gonna come closer to the football than they are short in the time. So the fact that you base your embeddings on what people actually do tends to reflect very, very well seasonality. There's an issue on aligning then the embeddings. Like if you think of training different products embedding across time, there's the issue of aligning them in the same space. But we didn't really find many gain by stitching together, let's say, 12 product pages, one for each month, instead of having, training the entire 6 months of product embeddings. So in the end, our practical solution, like our product-ready solution, is just the simplest thing. It's just train back to 6 months after, to 6 months before the day in which you are, and then you just do that. Again, remember that as a company, we provide this to other companies, which means that our trade-off between model simplicity and robustness and accuracy tends to be slightly different than what Amazon may have, right? Like Amazon really cares about being the most accurate possible, but they have one website. We need to be accurate, of course, but we also need to work for very, very different type of clients. In fact, a lot of our papers contain validation on very different type of traffic, different verticals, different products, and so on, because we need to prove to ourselves and to the, not just to reviewers, but to ourselves that this method actually scales across our client base. Elisabetta asked, have you considered an entity resolution to link data across e-commerce and augment the embedding quality? Well, just funny you mentioned that. So the paper Fantastic Embeddings that Christine mentioned has two parts, and she just covered the first one, which is how you produce the best possible embedding for a given shop. But now imagine you have two shops. For example, I don't know, you have Gap, so you have Banana Republic, you have Gap, you have what's called Atleta. Like you have like a bunch of brands that pertain to the same group, right? And now you can train product space for each of these groups and each of these brands. And the question is, can you align these brands in such a way that even if you train 3 different spaces, they actually look like the same space? And there's the second part of the paper, and the answer is yes. So what we actually did for the quality of the embedding, for the augmentation of the embedding, is that we have an unsupervised method, which is, let's say you train the embeddings for Gap and the embeddings for Banana Republic, and then there's a completely unsupervised way to actually align them in such a way that you can do basically personalization in one or the other space. And then there's a supervised method, which is kind of borrowing the idea from translation. In particular, since we have a cookie, so we can follow users between these two properties, let's say Gap and Banana Republic. Once a user goes between, she's searching for, I don't know, shirts in Gap, and then she leaves, and she goes to Banana Republic, we can follow her. And then basically we can treat the idea of moving from one space into the other as a translation problem. In the same way as, you move between English and French spaces when you do neural translation. Alexandra is asking, are duplicates common in online marketplaces you work with? Can they be an issue? There are duplicates, I mean the same product in 2 different shops? Yes. If 2 shops are actually competitors, it may be that they actually sell the exactly same thing. They just call it that like somewhat differently, or some of the metadata may be different. Like the image may be slightly different, the price may be different, the description may be different. It's not really an issue as all our models are per shop, meaning that no product base of client A knows anything about the product base of client B. So while technically some of these dots in these 2 spaces are going to be basically the same, there's basically no relation between them. Again, then there's a second question, which is, if you really want to find relation between them, can you find them? And like there's a detailed answer in the paper of how would you do that, and that's kind of related to the question before. But most of our clients are not part of a multinational group like Gap, which means they don't have multiple brands under the same umbrella. So most of our clients are just, different e-commerce doing different stuff. So for them, product spaces are just, are just what they sell. There's no relationship to what anybody else is doing. I think we answer all the questions in the chat, but we have surely more time if anybody wants to ask different question or curiosity or anything. All right. So thank you very much, Jacopo and Christine. And you say that the slides are online, but maybe we will follow up. We may publish the links and the slides also in our channels, so everybody will know where to look for the slides. And I hope that we manage at the end to finish the recording. So we will let you know if the recording was successful. I will share with you the links. That anyway, everything that we share is linked to the website of Data Science Milan. So you can just go on the website, give us a few days, and then you should find it. Okay. So thank you very much again. And yeah, I mean, if you wanna guys stay and ask any question, have a chat, you can stay. No problems. Otherwise, see you at the next meetup. Mario, thanks so much. The slides are we made the slides for this talk just to make sure, but they're gonna be, published in. We can totally share them. I can totally send you the PDF. You can put them online whenever, in whatever format you like, and you can distribute them. There's nothing sensitive about that. And there's all the links to papers, blogs, and other literature that I think people can consult if they want to, to know a bit more about what we did. Okay. For everybody else, if you guys want to connect with us on LinkedIn or email, we're very easy to find. And so, thanks again for your time. We hope to see you, sometime in the next talk, or maybe in person at the next, when when I'm allowed to be back again in the country. Maybe I can see you next time. I can actually see you all in person. Ciao. Thanks, Christine.
Thank you.
Ciao a tutti.
Thank you.